All right, so now, for the first time, I think, we're going to talk about vertical circular motion. Now, I know at the very beginning of the chapter I said we're going to talk about the water in the bucket, but that's kind of boring, you know? So what we're going to do instead is we're going to talk about motorcycles. So we are the physics consultant for Evel Knievel. So Evel Knievel is a guy, I don't even know if he's alive anymore, but he would do all these stunts. And so, for example, so this is a vertical circle, right? This is a track, and he's going to go on his motorcycle, and he wants to make this complete loop-to-loop. So this is just like the water in the bucket, but more exciting, you know? Okay? So we have to figure out what kind of speed he has to have so he maintains contact with the track and doesn't fall and kill himself. Okay? So that's what we're going to do. Now, he's going in a circle. So all we have to concern ourselves with are radial forces, right? I think I've been emphasizing that over and over and over again, okay? Radial forces. Okay, so here's 4 positions. What are the only radial forces acting on the motorcycle and the guy? Well, you know, there's just the weight and the normal, right? There's weight here and there's normal. What's the radial force here? It's not weight, right? Weight is not normal. I mean, radial. The normal force is radial. Here, normal and weight. Here, just normal. Okay? So that's it. Now, what do you think? Do you think that the normal force here is the same as the normal force here? No way, right? I mean, you know, here there's a lot of normal force. Here is not so much, right? But you want to make sure you're still touching the track, so it better be greater than 0, right? Okay, so we have 4 positions. We need 4 radial force diagrams. So, so you pause your video and draw the 4 radial force diagrams. Okay, we're back. All right, so here we go. And we can be kind of lazy how we draw this, right? And again, all we care about are radial forces, right? It's all we care about. Okay, so here, there's the normal and gravity. Here, the only radial force is normal. Here, look, they're both towards the center of the circle, right? Normal, because, you know, that's where he is, right? Normal, normal and weight, and here, just the normal, all right? Okay, so now we got to analyze each one of these things. Not so bad, don't worry. All right, let's do the first one. Let's do number 1. So we have the sum of the radial forces equals mv squared over r. You know, I got to put subscripts though, right? Because you got to admit, you know, you're going to have different speeds, most likely. So let's put subscripts. Okay, so that's true. So I write it down. Now I got to figure out what are the, all right, so now I look at my force diagram. So what are the radial forces at 1? This points towards the center, so it's positive. This points away from the center, it's negative. So I have N1 minus mg. Okay, so therefore, I can solve for N1 if I feel like it, which I do. So N1 equals mv1 squared over r plus mg. And, you know, that's going to be pretty large, right? It's not just the weight, it's also this, okay? By the way, what is this called? We've had that a long time ago. It's apparent weight. Remember that? Apparent weight. Apparent weight. Long time ago. Okay, let's do number 2. Number 2, we only have the normal force is the radial force, right? So that's all we care about. So number 2, sum of the, right? Write it down because it's true. What's the only normal force? N2. All right? All right, so that's it, right? So N2 is just mv2 squared over r. Here's N1. Okay, that was nice. Okay, let's do 3. sum of the radial forces equals mv3 squared over r. Now what is it? For 3, both of these forces point towards the center of the circle. So we have N3 plus, right, plus mg. Here we had minus because this was pointing away from the circle, but this is pointing towards the circle, so it's plus. Okay, then we want to solve for the normal. You'll see why in a minute. So N3 equals mv3 squared over r minus mg. Minus mg. This is the important one. You'll see why in a minute. Then 4, sum of the radial forces equals m4 squared over r, which is just n4. Okay. Now, remember, we're hired to make sure that Evel Knievel doesn't fall and break his neck and die, right? So, which one of these do we really want to concern ourselves with? Well, you know, we want him to maintain contact here, right? We don't want him to be in free fall. We want that motorcycle wheel to be touching the track, right? The inside of the track, okay? So in other words, we want the normal force, 3, we want this to be positive, right? If it's 0, he's in free fall. Good luck, right? So we want N3 to be greater than 0. Well, that's nice because look at the equation, right? If we want N3 to be bigger than 0, that means that this has to be greater than that, right? So therefore, mv3 squared over r has to be greater than mg. What cancels? Are you surprised? Better not be. So the masses cancel. Now we want the velocity multiplied by r. Take square root. Make it look nice. There you go. So there. That's all there is to it. So number 1, independent of mass. So if Evel Knievel eats a big breakfast, doesn't matter. You know, it doesn't matter the weight, the mass of his motorcycle. Doesn't matter what kind of clothes he wears. Doesn't matter. But he has to be going that speed, greater than that speed, in order to make the turn. Okay? So there you go. All right? So he pays you your $100,000 and have a good day. So this is basically the same type of analysis as you would do with the bucket, you know? I mean, it's similar, all right? Similar to this. All right. This is important. We're going to, well, you'll have some homework and maybe some exam questions about that, right? You want the normal to be positive. Okay, so we've just been doing, all right, so, okay, yeah, I just said that, right? All right, so I wanted you to really understand it, so if you can't read my hand scratching, at least you can read this, all right? It's important. Okay, let's review look, this is an example of non-uniform circular motion, right? I mean, the speed is certainly not the same. He's going fast here, he slows down here, you know? But anyway, this is non-uniform circular motion. So let's review non-uniform circular motion. So for uniform circular motion, you know, the speed was the same, so we never had any kind of a tangential force, right? But now, since we're talking about non-uniform circular motion, we have a tangential force. Okay, so let's review it. So look at, we're going in a circle, so we have to have a radial force. No kidding. The radial force causes the centripetal or the radial, why does it say centripetal? Radial acceleration a sub r. So you always have that if you're going in a circle. Now, we're talking about non-uniform circular motion, so either going faster or slower. So now you have this tangential force. So the tangential force causes the tangential acceleration, a sub t. Okay, so there's two forces, right? Two forces. There's the radial force that makes you go in a circle, and there's this thing that makes you either go faster or slower. So if there's two forces, there's two accelerations. Yeah, we know that. We learned that a long time ago, right? So this is the AR, makes you go in a circle. This is the AT, changes the speed. Yeah, let's read it. This AR changes the direction. A sub t changes the speed. Right? So if there's an AR here and an AT there, you can say there's a resultant A or a total A or whatever you want to call it there, right? Because the total A equals this A plus that A. And you notice that they added the vectors with a parallelogram method because it's easy, you know? It's easy to do that. And what would be the equation for the total acceleration? Well, it's just Pythagorean theorem. So the total acceleration, this A, the magnitude, right? What's this magnitude? It's just that squared plus that squared, square root of, right? So the total acceleration has a magnitude of AR squared plus AT squared, square root of, okay? So you got to be careful with the words, you know? I mean, if they want to know the radial acceleration, they have to say radial. If they want to know the tangential, they have to say tangential. If they want to know the total, they got to say total. They can't just say A. If they just say A, you say, what are you talking about? You know, what A, right? So they'll always, don't worry about it. I mean, they'll always include the adjective, so you know what in the world they're talking about. Okay, let's see, yeah. All right, so I would recommend you have this memorized. We're going to use it in physics. 121, 220, and also 221, you know, because electrons going around the nucleus and all that. So just memorize it. Yeah, I already said that. Okay, now we're going to do our really challenging, somewhat challenging homework problem. So you read it while I erase. Okay, the drawing shows a baggage carousel at an airport. Your suitcase is not slid all the way down the slope. It is go around at a constant speed on a circle, uniform circular motion, right? As the carousel turns. The coefficient of static friction between the suitcase and the carousel is 0.76, and the angle is 36 degrees. How much time is required for your suitcase to go around once? Oh, man. This is a good one. All right. First of all, is it uniform circular motion or non-uniform circular motion? Well, as soon as you see this, right, I would underline this, you know, constant speed. So it's uniform circular motion. Well, so without even thinking, what are you going to write down? Our good old friend, right? And let's see now. Yeah. All right. So you're going to write that down. Okay. Now, what are we supposed to find? It says the time for the suitcase to go around once. Well, what's that called? And we've talked about that in the past. What's the time for one complete orbit or one complete cycle of like a clock or something like that? It's the period, right? It's the period. So what we want is the period. It's not just any old time. It's the time, you know, for one revolution. Okay? Oh, boy. All right. You can do it. Okay. So let's see. What are the forces? What are the forces acting on the suitcase? Well, you know, there's a normal force, right? Normal force perpendicular to the surface. There's the weight. And again, there's friction, right? This thing would just slide down if there were not friction. So there's friction, right? So three forces. Friction, normal, and weight. All right, so we're going to draw the force diagram. But before we do that, maybe it would be worthwhile to get an equation for the period. Because, you know, I mean, we haven't really had an equation for the period, you know? So how are we going to do that? Well, I mean, there's a couple of different ways. So, okay, we know this is true, right? And we know it's true, you know, because it's circular motion. Right? We know it's true. But, man, where's a period, though? How can we get a period in that equation? Now you got to think, right? Now you got to think. Well, what's velocity? Velocity is the change in distance over the change in time, right? Okay. Now, what we want is the change in time to be a period, right? 1 period, okay? The period, so it's a special time. Okay, now what's the change in distance when the change in time is 1 period? So how far does that suitcase go around in 1 period? Well, circumference, right? Circumference. What's the circumference of a circle? 2 pi r, all right? Okay, so see, you got to figure that out because nobody's going to tell you, you know what I mean? You got to just think about what velocity is and what the period is. So what we're going to do then is we're going to substitute, right? So we have m over r times velocity squared. So we're going to square this thing. So we're going to have just 2 pi r over t squared, okay? And what is that? Well, it's 4 pi squared. Now look at, well, m is a pi, all right? 4 pi squared m. Here's an r squared, here's an r, so we just get an r over t squared, okay? So again, I mean, you know, you're not going to find that in a book. You just had to figure that out for yourself. And that's okay. We should be kind of used to doing that by now. All right, so we figured it out for ourselves. All right. Now, we better draw the force diagram, right? So I think I have it here. I hope I have it here. Oh, good. I don't have any room here. Okay, so look. So I'm saying that this is the carousel, right? This is the surface of the carousel. Okay, so here's our weight. This is the normal, right, perpendicular to the surface. And here's friction, right? And again, if this is theta, that's theta, you know? All right? And the friction opposes sliding down on the carousel. So there's my forces. And the thing is, remember, things going around in a circle, you know? All right, so now, you know, the order, I guess, look, we're going to have friction somewhere along the line, right? So, you know, you might as well solve for the normal first, okay? So let's solve for the normal. Let's use our z equation to solve for the normal. Okay, so here we go. So the sum of the z, now, what is the sum of the z's? What's the sum of the z forces? Is it accelerating this way? No, it's just going around like this, right, in a horizontal plane. So the sum of the z forces is 0. Okay, so what do we have? We have now, what do we have? We have n cos theta, right? Here's n, but we want this. So it's n cos theta. So we have n cos theta. But hold it, what else do we have? Oh, this is going to be kind of a mess, right? So we have n cos theta. What else do we have, though? We have fs here. So that's fs cos, that's fs sine. So we have fs sine pointing up. So we have fs sine theta pointing up. And then what's pointing down? Just the mg is pointing down. Minus mg. That equals 0. So therefore, let's just say mg equals n cos plus fs sine. Okay? All right, now let's keep, okay, so let's see. What's fs? Mu s n. U-S-N, right? And so we can just say that mg equals n cos theta plus mu s sine theta. Okay? And therefore, and right up here, therefore n equals mg over cos theta plus mu s sine theta. I mean, we're going to need it, so there it is, you know. Okay, now we got to solve the r problem, right? Because we got to use this, so we got to solve the r problem. That was the z problem. Now we're going to solve the r problem. Okay, ready? Here we go. So, sum of the radial forces. Now, I'm not going to write all this junk because this is what I want, so I'm just going to write that. Equals 4 pi squared mr over t squared. Okay, so what is it? Well, this is the center of the circle, right? Because that's where the r x points to. So I have Fs cos theta. And then here, this is n cos, this is n sine. It points away from the circle, right? N sine theta points away from the circle. Okay. Well, what's Fs? You know, it's mu s n. Okay. All right. Oh gosh. So n's a mess. Let's factor it out. So we'll have n mu s cos theta minus sine theta. Okay. Now let's plug in that mess. Okay. Let's do it. So here's n. So we're going to have mg mu s cos theta minus sine theta all over cos theta plus mu s sine theta. Okay, now what do we want? We want t, right? So let's put here, let's look at this and look at this. All right, so I want to get t, so we're going to cross multiply, or however, this is what I'm going to do. So if a over b equals c over d, then, you know, b over a equals d over c, right? Just flip them both. That's what I'm going to do, okay? Just flip them both. So in other words, I'm going to say, okay, so I'm going to say that t squared over 4 pi squared mr equals that crazy thing, cosine theta plus mu s sine theta all over mg mu s cos theta minus sine theta. All right, but then I'm going to multiply this by 4 pi squared, multiply it by m, which is going to kill this m, then multiply it by r, then take the square root. All right. Hope you caught all that. And I better put parentheses here, I'm going to be in big trouble, right? All right. Okay, so there you go. Now, wow, what do you notice? I mean, it's a mess, yeah, I know, but what's it independent of? What don't you see here? It's independent of mass. Doesn't that make sense? Yeah, it makes sense. I mean, this thing, you know, the baggage carousel works for high mass suitcases, low mass suitcases. I mean, you know, it works for all of them, right? Okay. So just plug that all in. And believe it or not, the answer is 45.3 seconds, which is kind of reasonable, don't you think? You know, just based on your experience at the airport. Okay. All right, so wow, that was kind of a cool problem. What was cool about it? Because I don't think we've ever done something like this before, right? You know, we had to find the period, and we just couldn't go find an equation in a book. We had to use our heads, right? We had to start with this, and then just say, oh my gosh, what's velocity? Well, velocity is distance over time, and then we just said, okay, if the time is t, the distance is 2 pi r. So you should expect to be able to do things like that, you know? You have enough knowledge, and you shouldn't have to just keep looking for equations. Just use your head, think, and you can do it. So that's why I really like showing people this problem, because it kind of extends your thinking, or I don't know, your problem-solving ability, okay? All right, let's do another one. Okay, let's do another one. Maybe not so bad this time, huh? I don't know. Let's see, it's going to be bad. No, it's not so bad. Okay, read it, please. Okay, a conical pendulum is formed by attaching a ball to a string and then allowing the mass to move in a circle. So let's just say I had a string and I'm going like this or something like that, you know? Okay. So what's the tension? What's the speed? Notice it says angular speed, omega. And then they're even being more, omega is radians per second, but they're even being rotten, they're going to say RPM. Rotten, right? That's okay, we can do it. Okay, so the ball moves in a circle. Agree? The ball moves in a circle. So we know what to write. Sum of the radial force equals mv squared over r, or mr omega squared. Yeah. Okay. So, but we got to draw the force diagram first of all. So let's do that. Did I do it? Oh, I did it. Isn't that nice? Good. Okay. So, you know, what are the forces acting on? There's weight and there's tension. That's really all, right? There's no surface, so there's no normal force, you know. All right? This thing is not touching the ground. It's in the air. So all you have is a tension and a weight. Okay, awesome. Well, okay. So, you know, we're going to say mr omega squared or something like that. So we have to know what the radius of the circle is, right? We don't know what the radius of the circle is. We know the string is 1 meter long, but we don't know what the radius of the circle is. So why don't we just do that, just get it over with. So here's the triangle, pretty sad looking triangle, huh? There's a triangle. This is 1 meter. And what is this angle? Oh, that's what we're trying to find out. We don't even know that. Oh, yeah. Oh, I guess it gives us the radius. I'm sorry. Helps if you read the problem. So this is 20 centimeters, right? So 0.2 meters. But we're going to have to figure out what the angle is. You'll see in a minute. All right? So, so let's see. So this is cosine, right? So cosine theta is adjacent 0.2 meters over hypotenuse 1 meter. Therefore, theta is cos inverse 0.2, just 0.2, right? And I promise you that's 78.5 degrees. Okay. We'll use that in a minute. You'll see. Okay, so A, what's the tension? So, you know, we have two equations, right? We have the z force equation and the r equation. Now, which one do you think is going to be the easiest to use to solve for the tension? Well, I think it's going to be the z, right? Because we're going to have t cos theta is equal to mg. Because remember, it's making a horizontal circle, right? So t cos theta has to equal mg. All right, so this is what I'm saying. So the sum of the z forces has to be 0. So therefore, t cos theta equals mg. So therefore, t equals mg over cos theta. All right, well, guess what? We know all that, right? We know the mass, 1/2 kilogram. We know g, and that's supposed to be a parentheses. And we know the angle because we just figured it out. Uh-oh, hold on a second. Oh, no, it's sine theta. I was looking at this, but this is the angle. So, sorry, it's t sine theta, right? Not cosine, because here's our angle. This is not our angle, this is our angle. Woo! Sine. Okay, so sine is 78. You know, just look it up. And that equals 5 newtons. So there's our tension, 5 newtons. Okay, now we want to get the angular speed in RPM. All right, we can handle it. So the sum of the radial forces equals mr omega squared, right? I'm going to use that because I want the omega. Now, there's only one radial force. What is it? It's just t cos theta, right? T cos theta. T cos theta. You write that down because it's true. T cos theta. Okay, so let's do it. So get rid of that. Divide by the m. Divide by the r. Take the square root. So 5 newtons cosine of 78.5. Mass is 1/2 kilogram. radius is 0.2 meters, square root. Oh, but wait a second. Okay, so this is going to, so the answer here is going to be 3.16 radians per second. And you know, I can see that this being a test question, this would be one of the possible answers, right? But it's wrong, because they wanted RPM. So this is good. That's why I'm doing it, right? Just to show you, just to remind you how to do that. So we want revolutions per minute, right? Revolutions per minute. So we don't want seconds, we want minutes. So we get to multiply by 1. So there's 60 seconds in a minute. So again, seconds on top, seconds on bottom, they'll kill, right? So now we have the minutes. So that's good. Now we want revolutions per minute. So 1 revolution equals how many radians? 2 pi. 1 revolution is 2 pi radians, okay? So seconds kills the seconds, radians kills the radians, and we have that crazy thing, which comes out to be 30.2 revolutions per minute, which most people just write as 30.2 RPM, revolutions per minute. Okay, wonderful. That wasn't too bad. One last, one more, then I think that will be it. Oh, and I'm just going to set it up. I'm not going to show you all the math. I just want to set it up. You can do the math. It's just high school algebra. Famous last words, right? Okay. A father stands at the summit of a large conical hill as he spins his 20-kilogram child around on a 5-kilogram cart with a 2-meter-long rope. The sides of the hill are inclined at 20 degrees. The father keeps the rope parallel to the ground, you know, the hill, and friction is negligible. Woo. What rope tension will allow a cart with a child to spin with an angular velocity of 14 RPM? Oh my goodness. Okay, but come on, uniform circular motion, right? You know, the cart and the child are going like this, uniform circular motion. So that's not so bad. But what's the first thing we have to do? You know, we got to get the force diagram. I hope I have a picture. Yay! Okay. All right. So this is the conical hill, right? This is, again, it's going in a circle. So we're going to say that this is the center of the circle, right? You know, in other words, all right. So this is the center of the circle. So there's our r-axis, points towards the center of the circle. Okay, what are the forces? Well, there's the tension on a rope. There's the normal force as always, and there's a weight. Okay. Now, it's a hill, so there's some angle. So this is the angle. So, you know, so this angle equals that angle. You learned that in high school or something. And if this were horizontal, this would be, the normal would be like that. So this angle equals that angle. So make sure you understand all the little trivial things like that, right? Okay. But you got to know that. You got to be able to figure out that angle stuff. All right. So again, we're just going to set it up, and I'll let you do all the details. Oh, notice they're being rotten again, right? Angular velocity of 14 RPM. So first of all, you have to convert that to radians per second, and you know how to do that. Okay, so I just want to write down the 2 equations. That's it. So the sum of the radial forces equals mr omega squared, because we want to get to omega there. So you write that down because it's true. Now, what's the sum of the radial forces? So again, we want things, so here, the t, this is t cos theta, right? T cos theta. How about this n? So there's the n, here's n cos, here's n sine. So n sine points away from the center of the circle. So we have t cos theta, that's this, right? This, and then that. And then minus n sine theta. Okay, that's it for the radial equation. And now for the z equation, we have, okay, now what is the sum of the z's, right? Remember, it's a horizontal circle. So there is no acceleration in the z direction. So the sum of the z forces is 0. Okay, so what do we have? Well, if this is t cos, that means that this is t sine. So we have t sine, we have n cos, and we have mg. That's it. So we have t sine theta plus n cos theta minus mg. Okay, so the rest is just math, and I'm going to let you do that. But I'll give you the answer. So the tension comes out to be 178.4 newtons. But again, you know, you ought to go through and make sure you know how to do this. You got to convert this to radians per second. And then, you know, you're going to have two equations, two unknowns. So you solve that however you want to solve it. You know, substitution or whatever method you've learned in high school. Okay, so that is the chapter. Let's review. All right, we did two-dimensional trajectories a long time ago, sorry. Okay, I mean a long time ago. We now understand the dynamics of uniform circular motion, right? If there's a circular problem, it has to be a radial force, which equals mv squared over r or mr omega squared. We talked about orbital motion, and we did Evel Knievel motorcycle because it's more exciting than water in a bucket. Okay, whenever you do a circular motion problem with forces, it's much easier if you use this Ritz coordinate system. And you notice we never tilted it, right? Don't tilt the Ritz coordinate system. It's going to make it harder on you, right? So just use this coordinate system. Again, and there's nothing new here. If there's friction, solve for n. And use Newton's second law. This is always true right here. So you just write whatever part you need, but then you have to figure out what are the radial forces, you know. Oh my gosh, look at that. Horrible. Okay, you've seen this before. You better know this. S equals r theta, because then you can get v equals r omega and all that other stuff. You better know this too. A sub r equals v squared over r. I already talked about that. Okay, the definition of velocity is dv dt. In angular, omega equals d theta dt. We had that a long time ago. Velocity, what? Oh, no, that's dx dt, sorry. Okay, the tangential velocity is ds dt, right? This here, omega, is radians per second. The tangential is meters per second, so ds dt. We know that distance equals speed times time. If we're going around a circle and we know the period, then the distance, circumference, 2 pi r, equals velocity times period. But now let's do it in terms of angles, right? So now we can say this. We can use the angular version of this. We can say that 2 pi radians equals radians per second times period, right? I mean, don't memorize this. You should be able to figure these things out. If you know this, you just differentiate it to get that, right? We've been using this all the entire chapter, right? Sum of the radial force equals MAR, which equals mv squared over r, or mr omega squared, right? This is a long time ago. Alpha, d omega dt, d squared theta dt squared. Okay, this is AT equals r alpha, which you just get from differentiating this. Kinematic equations, there's just like the regular 3 kinematic equations but if you're doing a circular motion problem, you just use angular variables, not not like x's and v's and stuff like that. And I already said this, right? Often it's useful to use this. Well, we're going to use this like crazy in this chapter, right? That's what the whole chapter is about. Sum of the radial forces equals mv squared over r, or mr omega squared. So that's kind of a big summary thing, you know. So yeah, you really should memorize this. You can kind of just figure this stuff out. It's up to you, though. That's it. Thank you very much.